No. Anodes. These are anodes, okay? Where X-rays are made on this. Okay? Now, you see the pitting on the face, everybody? You see it? The pitting? See the pitting? See the pitting? Now that pitting is normal wear and tear, or normal operation. Now I'll come back and I want you to look at the, well, it looks like they're gouges. Do you see the gouges? See the gouges?
Mhm.
Looks like somebody dug them out with a chisel. That's when what didn't happen?
When it didn't spin.
It didn't spin.
You're talking about like these.
Yeah. Mm-hmm. That's when it didn't spin. And guess what the anode took there?
A lot of direct electrons.
It took all the electrons on one spot. And what did it do? It what? What's the major occurrence here?
Heat it up.
It melted it. In other words, this is tube failure coming. Where it didn't spin. Those electrons just hit on one spot. And in time, the tube will blow. All right.
How often
The
do they have
anode.
to be replaced?
Pardon me?
How long do they last?
And about 5 years. Normal wear and tear. Now, if you work in a clinic that's not busy, okay, they'll last longer. Now, a little bit more on the pitting. That pitting is normal wear and tear. But the X-rays, believe it or not, can get stuck in there. Okay, they can get stuck in there. And they can't get out, so your output is less. So, there's your anode, right? Electrons bombard it, and radiation is produced. Now, let me draw this a little better. I just put an angle on that anode, and you can see the angle on these up here. They have like, they're beveled off. I'm going to talk about something called the anode heel effect. So let me draw a few electrons here. They bombard the anode and produce heat and radiation. And the radiation goes all over the place. Like I said, what we care about is what? The stuff that comes out of the port. All right. So here's the anode heel effect. Like I said, it goes all over the place. Now, if you want to go this way, you with me? I mean, it can go this way, it can go this way, it can go this way. But what if it wants to go that way? It can't. In other words, radiation can't go that way because the anode's in the way. That's called the anode heel effect. That affects beam intensity. So let me make a statement about the anode Heal effect and beam intensity. The intensity of the beam will be greater on the X-ray beam. The intensity of the X-ray beam will be greater on which side of the tube? There's a word missing. I want you to fill it in. The intensity of the beam will be greater on which side of the tube? Somebody guess.
Photon beam's not made till it's
The cathode side?
On the what?
On the other side?
What side is that?
The cathode?
The cathode side. That's the word. The intensity of the beam will be greater on the cathode side.
I was not even close.
Yeah.
I know your wheels were turning. Because you see of what's called the anode Heal effect. It's going to be weaker. than here. All right, that's the anode Heal effect. And of course, in your notes, did you guys put down the polyenergetic beam concept?
Not yet. I mean,
No?
we've talked about it in other classes.
Did I draw it? Okay.
A polyenergetic.
Polyenergetic beam, all right, so. Does this look familiar? Huh? Does this look familiar? I'm drawing a what? Very good, polyenergetic beam. Now, coming out of the port, this is a filter. It's aluminum. What does it do?
makes a uniform beam.
It's an attempt to make a uniform beam. So in other words, it filters out long wavelength radiation that would only, so you're familiar with this, that would only be absorbed by the patient. That radiation that's filtered out is not what we call image producing, but a lot of it comes through. So here, what am I drawing? I gave you a hint here. Patient, so it's in the body. Now I'm really gonna look at that image over there. What's in the upper right corner? What's that look like? What spine? Lumbar spine, right? You know it's lumbar. Do you see the pelvis?
I thought you were talking about the. I was like, I don't know what that is.
That is called a viewer. Okay?
No, I mean like the little thing sitting on the hip. The circle.
Looks like a bullet.
Maybe it is.
I was like, I don't know what that is.
See, you go right to the gore.
I watched Saw 5 last night.
Yeah, that could be. That's an old timer though. There's a lot of arthritis in that spine. Yeah.
That would be very unfortunate.
Hey, now, wait a minute. Not that he could have been a World War II vet.
That's true.
Unfortunately, I'm not
All right, so what did I try to draw here?
It's fine.
Thank you. This is the lumbar vertebrae, right? So the body, the transverse. Oh, I know what I forgot. I forgot to mark anterior and
Oh, that makes
posterior.
it so much more clear.
Spinous process, transverse process. All right, so we've got radiation coming through.
Are you gonna ask us to draw this one?
No, I don't think so. I do have 2 weeks to decide. So the radiation strikes the patient, all right, and it can, this X-ray photon went through, okay? It penetrated the patient. That's always a good thing, right? Because we didn't leave any energy in the body. And it strikes something called the image receptor. And in this case, over on our viewer, the image receptor was what? Film. And when you look at this image, you see what? White and black, and some gray, right? That one that went through there and struck the image receptor looks like what up here? Black. Okay? This is all the radiation that penetrates. All this radiation here did what? It was absorbed. So now I'll draw one of those up there. So the ones that go through give us a density, and the ones that don't, like this one, it gets absorbed. What does absorption look like on the image?
Contrast,
Pardon me?
the white contrast.
Yeah, and as long as you brought that up, Steve, we have, you a photographer? Are you?
You got an Instagram?
So you see, when you have the black to the white, it's called what? Contrast, which is a difference, right? Like you can have contrasting opinions. Do you ever have that with anybody? Of course. All right, so let's talk about this one. Those that are absorbed. Okay? And give us what type of radiographic appearance? What?
White.
Louder?
White.
White, okay. This is called did you guys know this?
Absorption.
Have you heard of this?
We did this one last time.
Did you? So you know what this is? Photoelectric effect?
We could use your.
Oh,
I
okay.
could use your-
Yeah, it's always good.
Yeah, we can always use a refresher.
All right. So, now we got to go back to, I think probably class number 1, atomic structure, electrons in a shell. Okay, they're held there by a type of energy called binding energy, measured in keV. All right, photoelectric, here's your key to remember that. Is it coming back? The photon hits a tightly bound inner shell electron. And what happens to that electron? Put it in
It
words,
leaves.
Steve. Huh?
It leaves.
It gets ejected.
Yep.
So now what do we have? We have a free electron. The photon is completely absorbed. And what about the atom?
Unstable.
It's unstable. So what do we have? We have something called well, what is it when you have two things? A free electron and a unstable atom. Ra. They're a pair. Okay? They're an ion pair. So the photon's absorbed. When you look on that viewer, it's the white. So what does that? bone, right? What else?
Cartilage.
No, not cartilage. Mm-mm. Teeth, and then what else with teeth? Fillings. All right, what else? Look at that thing. What you guys think that thing is? Bullet? Metal, right? High atomic number. What's it doing? It's absorbing. So you guys heard about photoelectric effect? All right. Now you see it on the view box. Now you can see it. All right, so that's one. So the electron gets kicked out. It's floating around. We got an unstable atom. And over time, what does that free electron do? It finds a home. Pardon me?
It'll lose energy.
Oh yeah, it's very, so here, let me, did we do characteristic radiation? Have you heard that term?
I have.
Another review? Quickly. These are shells. These are electrons. Inner shell, absorbed. Free electron, ion pair, unstable atom. This electron jumps in there. This electron does what? Jumps in there. We've got an opening here. What could jump in there? Or from somewhere else. And every time an electron goes from a shell, it creates a little photon called characteristic radiation. Too weak to do anything. We don't care about it. It just happens. So, an electron lands back in there, and everything is now what? Stable, but the photon was completely absorbed. Do you remember another X-ray interaction with matter? There are others, but oh, wow, it is. All right, somebody spell. Is it L-O-O-S? How's that? I don't see anybody going to their phone for me.
Oh, I got you.
That's not spelled.
Loosely.
Don't look at it too hard, you'll.
And then loose.
Yeah, I get
Yeah,
ahead.
don't do it.
Is it right? Huh.
I think so.
Thanks.
Correct.
All right, so the other one is called the what? Have you heard of this? Compton, right? Compton involves a loosely bound outer shell. Here's our shells again. Loosely bound outer shell. Photon comes along, hits it. What happens to the electron?
Down.
It gets ejected. It's free. Now what happens to the photon?
Absorbed. No. It also leaves. Right?
What?
It's redirected.
It's redirected,
Yeah.
okay? It gives up some energy and then it gets to be a longer wavelength. Again, eventually someone will fill in here with an electron, but what is this? This is a what? This is a Compton scattered photon.
So it's lower energy than it originally was before it hit the electron.
Oh, it gives up energy, yes. It's scattered.
Equal to the amount of energy
Right, it's all the numbers would add up. But why do we care about that?
Because
Because
it
it
can mess up our
adds static to your picture, makes it blurry, fuzzy.
Let me clean that up. Sounds like you guys heard something like that? You see how that's nice in black and white? That's what we call high contrast. Okay, it's kind of like this. This is high contrast too, right? Black and white. That's high contrast. The scatter, imagine that image with a grayish laid over it. Grayed. Wouldn't be so pretty. That's what scatter does. It dulls and it grays the image. What else?
It can also hit
Why
people.
else do we care about this?
It can also hit people.
Hit somebody else.
Hit people?
Yeah, that's why we wear a apron. Okay, that's why we wear the apron. And the apron will absorb that as a photoelectric, right? Because think of it. It hits that apron, does it penetrate?
No.
It's absorbed, right?
Yeah.
That's what? Photoelectric. Yeah, it's funny, when I learned this, we learned this, but I don't remember anybody ever translating it to the image. All right, there are other, did you guys study any other X-ray interactions with matter? Isn't that neat? Because I'm sure you were all shocked to hear there's something called a positron. Remember, what is that? A positive electron. What? But that's an interesting phenomena too, because we have energy and then we have matter and then it goes back to energy. But do we deal with that? Do you guys deal with that in therapy, did Jane say? Does your linear accelerator do that? I don't think so. But it's really not something we use in healthcare pair production because it's measured in what? That's pretty heavy stuff. All right, pair production. What you need to concentrate on is photoelectric and complex. All right, so let's talk about this now. The image receptor. And there's one on the board. That is what? What type of image is that? It's film. Okay, have you guys ever differentiated these two words, analog from digital? Are you familiar with that? Okay, let's talk about the clock. Which is which?
The digital is, you would see it like that.
When you see a number? Analog is what? All right, so let's move it now to imaging. That's a what? We're guessing? We're guessing what? That's analog.
And digital
Images
has,
on
like,
film.
An imaging plate.
Pardon me?
A digital would have like an imaging plate.
Well, so would a film. They both have plates.
Like a computed.
We'll get to the, okay. You're on the right, you're in the neighborhood. They're both produced from a plate or a cassette. Okay? Look at that thing. What's the dimension? How many, what by what?
4 by 16 or something.
That seems right.
That's the size, 14 by 17. So we would have a cassette. Imagine this being a cassette. We put a piece of, and it was 14 by 17. We put a piece of film in it and close it. That's analog imaging. Film radiographs are referred to as analog imaging. Compared to what now, guys? What do radiology departments do now? They produce what? Digital images, electronic images. There's one scenario. Okay, there's something called computed radiography, or they call it CR. That is the cassette that you take, and you're going to need to know this for the exam, and you put it into a reader.
Looks like a big printer. It looks like a big printer.
It does. Looks like a big printer, like a kind of a refrigerator like too. So you put the cassette into a reader. And the reader will open the cassette, scan it, process it electronically, and give you a
Image.
digital image, right? That you look at on a monitor, yeah. Then there's another one. Digital radiography, guys, no reader. No reader. That's in the table. When you're up in the lab, upstairs, there's 2 tables up there. For DR, it's all in the table. You just need to get the anatomy over it. Okay? The one in the private room with the big window, that's DR. So it's exposed and the image pops up immediately. That's digital imaging. Now, these things all have advantages. The digital from the analog. With analog, you get one shot. Do you guys ever take pictures with a camera with film?
Mm-hmm.
Remember those days? You'd take that film in and you'd do what? Or you'd get it back and you'd go,
Mm-hmm.
I sure wish it came out. Remember?
You certainly thought more about what you wanted to take.
Yeah.
Before you just said.
Oh yeah, compared to digital. All right, so it's all or nothing with film, photographic film, radiographic. With digital, this stuff here, guess what we can do? If it's a little light or a little dark, we can what?
We can change the brightness.
What do you call
Editing.
it? We call it tweaking.
Oh.
You can tweak it, make it darker, lighter. It saves repeat, saves needless exposure to the patient. One of the greatest things when you went from that, you guys ever watch these medical shows where they have residents and you know the attending's walking around and what's behind he or she? Posse, right? And who are they?
The interns.
And the residents and the fellows and maybe a medical student. With digital imaging, you don't see that so much. I mean, they're still together, but you don't see them walking around as much, especially walking the imaging, because they don't have to go down and pull a film out of a jacket and put it. They don't have to.
Send it.
What do?
Pull it up on the computer.
They pull it up on the computer somewhere. Okay? So that's a really nice advantage. Instant image. Now, the exposure, you might see, I've seen ads on TV where these people are hyping their new digital technology. They like to say that it's minimum exposure. It's not what it appears, in other words. In order to get a digital image, you got to have so much radiation to start the process. And if you don't have enough radiation, tell me what I'm drawing here.
Bird. It looks like a Tweety bird, okay.
Lateral skull. Now you see. Skull, nose, lips. Here, oh, I forgot the
I was
Wait,
gonna
That makes it so much
All right, there you go. So if you don't give it enough radiation, you're gonna get
Grainy image.
It also looks like another net.
a grainy image, because so you gotta give it a,
And then a shot.
no, just a little more exposure than normal. Yeah. Pardon me? You guys throwing these big word contrast and sharpness. Okay, so yeah, in other words, the technical term for grainy is something called quantum
I don't know.
quantum model. Now, when you're watching, any questions on this so far? When you're watching TV, especially with the streaming concept, every once in a while a signal might get hindered or held up. And what happens to your image? It gets, what's the word I'm looking for? You guys don't know this word. What's what? Choppy. Oh, I like that.
Pixelated.
It gets pixelated. Have you ever seen that? Where the face becomes what? A bunch of little squares? Yeah. That's kind of where we're going next, okay? Now we're talking about viewing the image on a computer monitor. You guys all comfortable with what a matrix is?
In bonds?
Pardon me?
I know what a matrix is in bonds. Never mind. It's not
Did
the
you
same.
say bonds?
Yep.
As in investment?
No.
Oh, bombs.
No bonds, like metal and like
Oh, okay.
honeycomb. No.
All right.
Matrix is your investment.
All right, so when you look at a monitor, so you've all seen these pixely things, right? Doesn't it drive you crazy? Hope that goes away soon. If that's a monitor, this stuff is all demonstrated. That's enough. But this is a what? Every one of these is a what? A pixel. And something happens to it, right? And your image gets pixelated. So a matrix is a series of pixels. The smaller the pixel, the greater the sharpness to the image.
Why 4K TVs look so good.
The what?
The 4K TVs look so good.
4K TV. But on the other hand now, So the smaller the pixel, the sharper your image. But you guys, well, let's talk about when the concept of your digital TV first came out. Things all had to line up. So in other words, your image had to be transmitted digitally. It had to be received digitally, in other words, could be processed. And then you had to have a TV that could demonstrate digital TV. Are you with me? In other words, all these things had to line up as part of the digital family. If something's missing, you don't get a good digital image. For instance, maybe some of you can relate to this. Comcast TV, anybody here have Comcast? Anybody? Okay. You've heard of it, right? All right. So with Comcast, you get a lot of channels. Some of the channels, you've heard of the channels here in town, Channel 12, Channel 4, and all that. So when you're on your TV and you click in Channel 4 or Channel 12, okay, you're not going to get a digital image. Okay? Oh, you'll be able to watch, but if you have the digital converter and all that, you'll click in 412, channel 412. That's digital, and it's so much sharper. It's so much sharper. Because my wife will be watching something that says, you could get a better image, better picture if you go to this number. Oh, yeah, that's pretty nice. All right, so things have to all line up. Okay, so matrix. So when you see a matrix, let me give you some matrix numbers. 64 by 64, 64 this way, 64 that way, or 256 by 256. The bigger your matrix, the sharper your image, okay? The bigger your matrix, the sharper your image. Another thing, this is a nice thing, that image there, that's an analog image. It can be digitized. It can be digitized and put on a what? CD. So you can get analog images digitized and burned into a CD, and some people will do this. They'll take those images to their doctor and they'll view them with their doctor. So remember, digitizer converts analog to a digital image. You guys ever seen these things? Something like this? What is this? What is this called? A what? Oops, sorry. A film jacket, right? You put what in it? Film, right? And so you've got all these analog images. And so what do you do with these analog images when you don't need them?
File them away.
You file them away, okay? Now, being a radiation therapy student, do y'all know what paying your dues is? Have you heard of that?
Like initiation,
Pardon me?
like an initiation.
Well, it's kind of that. When you guys are going to eventually get into a department, right? Guess where you're going to be on the totem pole? At the bottom. Okay? You're going to be doing what? paying your dues. Guess what? We've all done it. We've all done it. And it's just part of it. You guys will be running linen, emptying linen bags, but as time goes on, some first-year student's gonna come in behind you. So my point is that before we had digital imaging, we had a lot of what? We had a lot of these. And guess what radiography students did back in the day to pay their dues? File these away. Now here's how you get through paying your dues. So I knew when I was a first-year student, way back in the day, I knew that every Thursday afternoon in clinical, we were gonna be where?
The record room.
In the file room, in the bowels of the hospital, doing what with these things?
Organizing, putting them
Putting them away. But this is how you pay your dues. So we're down there. Is that pizza?
Pizza.
Is that music I hear? Yeah. And then all of a sudden, Cokes appeared. So what did we do? We made it a what?
Party.
And we still filed them away. So that's how we paid our dues. We made the best of it. As long as they got filed, it didn't matter. We weren't disturbing anybody. So yeah, remember, paying your dues is so far from physics. But you guys need to know this stuff. And who pays the biggest dues? Well, who's at the top of the total? Guys, doctors, right? They pay the dues. Real big. Real big. Do you know what it takes to become a radiation oncologist and all that? Did you ever go over that? The route they take? Should I do it?
Yeah.
All right, so we'll go over this. So, this is just an exercise in numbers. Of course, that's physics. How old are you when you finish high school? 18. This is going to be the chronological journey a physician takes. All right, so then what do? You go to where? College. How long is that?
4 years.
So now how old are they?
22.
Then you go where? Medical school. How long is that?
8 years.
So now you're 26 and you're really just kind of a general doctor. And then if you want to be a radiation oncologist, you got to follow that trail. In other words, be a resident. Now I think they might have to do some time. That could be 4 to 5 years. In other words, you might have to do a year or some years of internal medicine, you know? You've heard of this? Have you heard this scenario? For what, an oncologist? So now how old are you? 30, 31? When you're all done, you're board certified oncologist? And you're ready to do what? Go to work. So look at those numbers, guys. Look at yeah, from here. See these years here? I can tell you, these years here, your 20s, they're some of the best years of your life.
I'm already falling apart, so I'm just saying.
I think it's supposed to be the best.
Well, but when you're on that trail, you're giving up a lot. You're giving up a lot. Somebody's going to a concert, what are you doing? You're in the library on Saturday night. That's paying your dues for starters. And when they're here, when they're doing that 4 to 5 year residence, they're putting in some long hours. That's what I mean. That's how doctors, they pay their dues. I'll tell you a story about a resident here in town at UF Shands. We have a radiology residence. And I said to one day, I said, hey, He was graduating, he was finishing his residency, he was about 31 or 32. He says, hey, you gonna do a fellowship? You know what that is? Have you heard of that term? It's just another year of training. For a radiation oncologist, a fellowship could be one additional year where they go somewhere and they just treat certain things, and then they become the specialist in that. I said, hey, you gonna do a fellowship? He said, absolutely not. He said, look, I'm 32 years old. It's my turn to make some money. He took a job as a radiologist. He said, it's my turn to make some money. Everybody I went to college with, they've been out for years making money. And he says, you know what, it's my turn. And you know what, he was right. He paid his dues to get there.
How does everybody go?
Question?
Yeah, I guess so. I was just saying, how does everybody go to college without already?
Oh, well, let's face it. All right, so let's say his buddy went to law school. You can be 25 and be a lawyer. See, or an engineer. Or an accountant. He said, no, it's my turn. All righty, one last thing. These digital images are stored electronically. Have you ever heard of this acronym? PACS? Have you heard of that? It's PACS. It's an acronym and it stands for Picture, Archiving, and Communication System. And that's the big bank where electronic images are stored. Any questions? All right, so you're off next week. So when you come back 2 weeks from today, what?
Test. Last test.
Pardon me? Exam 4.
Do you think it's too late for us to take that route? Well, we would have to get a bachelor's in science,
To do what?
become an oncologist, go to med school.
Oh, that. Yeah, to go to medical school, they really want you to have a bachelor's degree with a ton of science. Yeah, and then it's competitive. Grades. I don't know if too many people work part-time job in medical school.
What about working part-time? Well, I guess it's up to you. I don't know why I'm asking you. Like getting a bachelor's in science, what do you think about like working as a radiation therapist?
A bachelor's degree as a radiation therapist?
Yeah.
That will open doors for you in terms of what do you want to do? I mean,
You mean like going to school while working as an RT?
Well, yeah, both. but
Well, yeah.
I-
I'm sure people do
Well,
that.
some of the hospitals will pay for that.
Yep.
Like you can get a bachelor's in it, and they'll
Oh,
pay for it.
shoot, maybe we should do that.
Yeah, the bachelor's will open doors for you in terms of maybe you want to manage a department someday.
Get a master's in dosimetry, a bunch of different things.
In other words, or there's kind of a trend to get people with an MBA, Master's in Business Administration. They're not radiation therapists. Okay? Somebody's going to have to teach them the business. Okay? People like you. They don't know the technology, but they've got the business sense to manage the budget and so on. So, yeah, the more education you get, the more doors open. But some people are fine treating patients. I mean, that's their calling. No, you know, it's, the career that you guys have chosen, it does have one perk. Well, it has several perks. You know what they are? I think you guys know this already.
Most of the time, it's just an 8 to 5 job, and you're off on major holidays. It's a good family job.
No call. I think you all know what that is, right? Maybe once in a while, you'll take call. And the patient may be in crisis, or you gotta go in and assist the doctors. It's conducive to family life. Same as the one in imaging, mammography. That's pretty much Monday through Friday. All right. All right, you're gonna need to study everything we talked about last week. The tube components. Don't confuse stator from rotor. Thermionic emission. Matrix, pixel, CR and DR. Okay, that image. You see there's two X-ray interactions with matter up there, right? To get an image, like on the viewer, which is more important? Photoelectric effect. Just think if we didn't have that. Would we have anything? Would we?
Everything comes affected.
Yeah. So I have a physicist friend, and he refers to the photoelectric effect as money. He calls it money, because without it, where are we? Right? You gotta have that. It's money. That make sense? I guess, could we call that a statement pop culture? No?
Sure.
Okay, thank you.
Whatever you want.
All right, so guess what I have for you guys? Any questions? You're gonna walk out of here with all your tests back.
Jeez.
I know it's about time.
Sorry, guys. But I appreciate your patience.
That's okay.
You're good. This is always his place with big things.